You got me when I first. I was like, wait, what? I thought myself, I thought it was a metal alloy, but initially also again, a metallic and a non-metallic. The non-metallic carbon, and the metallic part is tungsten. Right, correct. So the question was, for example, iron oxides and things like that, are those considered ceramics in this? So if it's nitride, sulfides, oxides, all of those.
Yeah, essentially, because first you do the FE, then you'll do the P, and you get your license, and then you can stamp the documents, and the company will pay for that, right? There's a material sections to that. There are two ways to teach material science, and so far, we're gonna do the classic way, which starts with this kind of layout. So it's the electronic structure of the materials, it's the atomic structure of the materials, and then basically we're going to say that all of the atoms are treated as different size of balls. That's what you're going to see in the lectures coming, you know, ping pong, tennis ball, basketball, relative sizes. And then how it's all being put into a structure, right? To control the process, to control the structure, to control the properties. And then discuss the defects and equilibrium in phase diagrams. The phase diagrams is the holy grail. And kinetics and diffusion. So the cell phone that you have, or the laptop that you have, was put together because there's some microchips in there that are all assembled together in the microcircuit, and they went through what's called a reflow process. And obviously we get kinetics, diffusion, mechanical properties, elastic deformation, fracture, plastic deformation, dislocation, and strengthening mechanisms of how to make materials stronger. The Liberty ships that I told you about, there's one in the port of Tampa. It's a great exhibit to visit. This is a brand new ship that got deployed, and what we didn't know about it at the time, or the humans didn't know much about, what's called a ductile to brittle transition. And it goes back to this experiment that I described to you, where you take a tennis ball, you put in liquid nitrogen, and you drop it on the floor, and it shatters like glass. So 25% of those Liberty ships had cracks in them, and main reason was that they had to be built very fast during the Second World War, and they used welding, and welding joint provided a continuous path for the crack to propagate before they used rivets. So the crack would propagate from one rivet to the other, and then would stop. Deterioration of a mirror. If you go to the bathroom, pretty much any bathroom at USF, you're going to see that the bottom of the mirror is delaminated. Okay? You don't see the delamination on the sides. You don't see it on the top. So this is a combination of a thin film in the back of the mirror that provides you the reflection, and the fact that people, when they wash their hands, they're sprinkled with water, and water reduces the adhesion. Another example is a Boeing plane, and you can see there's a reflector over there, and the film delaminated. You can see flakes of that film on the bottom. This is probably one of the cooler examples where the device still continued to work, even though the film failed. Something like this happens in your calculator or your processor, in a cell phone or a laptop. That's not going to be okay. And what you see here on the bottom are some nanotubes, and these are 4 atomic layers of gallium arsenide. where allegedly we're supposed to see quantum effects, but there's continuum mechanics that describes how this is rolled into a structure. And then those atomic defects can propagate to a very large scale that you see over there in the Club Ray in Krakow. And you can see the film that's being stretched, and certain stress concentration points it ruptures, and in other areas it delaminates, and there's buckling delamination. So we start from the atomistic scale. You can see over there's a crack of 0.6 nanometers, and that's 6 angstroms. That's roughly interatomic distance. So it all starts at the atomistic scale and eventually propagates to a very, very large scale. So material science is not just about the process, structure, properties, or relationships. It's also about trying to find a length scale. What is the scale at which certain phenomena are happening? And by the way, what you see there on the right side is a chip that Motorola still makes. It's a 2x2 millimeter power amplifier. It has 6 transistors, and every cell phone has it. There's about 25 microns of gold, and this thing sells for a couple of dollars. So you can imagine the scaled economy. How can they make profit by selling it for $2 when there's 25 microns of gold on it? The famous process, structure, properties, relationship triangle that we've been talking about. Process: casting, stamping, forging, deposition. Structure: microstructure. So we need to have some sort of microscopy to look at a very, very small scale and find that length scale. And that affects the properties, dielectric, mechanical, whatnot, to control the process, to control the structure, to control the property. Classes of materials that we discussed. Again, there was Mike Ashby, who came up with the new way of teaching materials in terms of the selection of materials. Like we discussed the beverage container, right? It can be plastic, it can be metal, it can be glass, right? The same thing for your gadget. You know, you have a laptop. Some case is made out of some alloy, so it's metal. Some is plastic. And there are some advantages or disadvantages of using different materials like that. He also introduces shapes, which has to do with mechanical performance. And shapes are important because you can see, somebody asked me about the airplane. Okay, this is the wing of an airplane. Can this piece of paper support its weight?
No.
Okay, what about now?
Barely.
A little better. What about now? Now, at some point, this becomes a weapon, because it is a weapon. So there's only one kind of loading configuration where it doesn't matter. Obviously, like for bending, even for compression, it matters. But for tension, this wouldn't matter, because I can pull on this or I can pull on the whole thing. It makes no difference. Okay? So depending on how the material is loaded, then you have to worry about the performance. And you can improve the performance by like a factor of 100. Metals, polymers, glasses. Question is, what are there other classes of materials, and natural materials that have a different class, or different kinds. Composites. Composites can be man-made or they can be natural. Composites also mean that the properties are anisotropic, meaning that they are different in different directions. And that $1 million question, actually $50,000 question, and $100,000 and $150,000, it's just an older slide from Stanford that shows you the yield strength versus the cooling rate. 3 pieces of steel taken out of the same furnace, same pieces of steel that were cooled in. And what we did not emphasize yet, but pretty much the rest of the class is going to focus on, is the microstructure. So what you see over there is the microstructure of what was cooled at different cooling rates. And you gotta have some sort of magnification device or microscope to look at that. But that is the reason why. So we'll talk about the mechanisms of failure, what we mean by failure, why materials fail and how they fail. Every time you slam the door in your car, you want to be able to open it. If the geometry of that door changes somehow, that door would not latch next time, right? So that's one of the design criteria, is to just have elastic deformation. I already showed you a similar slide, but on the right you see cold worked metal versus recrystallized, and also we're going to discuss what that means. How many of you use a pencil and a paper to write something? Why do you do that? So that you can erase, right? You can easily erase your pencil writing. The processing history of the metal can be erased by the heat treatment. And I told you that we're looking at some dimensional scale. So there's transmission electron microscopy of the nichrome alloy, nickel chromium alloy. Does anybody know the application of the nichrome? Huh? No, it's not Inconel. Nickel chromium. Do you have a stove? Is that an electric stove? Gas? Does anybody have an electric stove these days? Okay. What's the heating element there? Coils made from what? Aluminum. No, aluminum has a melting temperature that's way too low. It's just gonna melt. Yes, the heating element made it from what? Yes. How did you figure that? You had no idea, but you're right. Okay. What is the difference between this one and that one? Look at those two images. One is cold worked, meaning that it's been forged and deformed plastically, and the other one is recrystallized. Well, yes.
I was going to say, the one on the right has a lot less cracks, and the fractures that there aren't as long
Yeah.
as the
Those are not fractures. Those are not cracks. No, those are dislocations. Dislocations. And we're going to talk about what dislocations are. Do you guys have another class after this? Are you going to go home? Are you hoping to go home around 4 p.m.? Why? So that you go home before traffic. Right? This is traffic. This is 5 p.m. This is 4. So.
And it depends on the highway.
No, it's true. Because what happens is those dislocations are generated within the material. The atoms physically, the atomic planes physically move. Those are cars around USF at 5 p.m. on the left. But you just wait another hour or two and you go to the right. Or you can heat things up, and that's the process called recrystallization. We already had that graph of iron plus 3% silicon. It's a little bit of salt that you sprinkle on your whatever you're going to cook tonight. Make it more tasty. And then on top of that, you can change the rotation of the rolling. So the rolling and processing creates deformation texture. And all those grains, they get like, have you ever played with silly putty? And that gets stretched in a certain direction. So if you start rolling it, there's going to be deformation texture. And that's how the processing works this thing out. So composites, I did my master's thesis on the first system of aluminum matrix and boron fiber. Boron is very brittle, but in the end, there was material, pipes, that are made from aluminum, so they have the density of aluminum, but the strength of steel. Super expensive, but that's a construction element of a satellite system. Aluminum matrix boron composite. Or a shell of a rocket, for that matter. We talked about ice age and whatnot. This is a relative evolution of the material graph that shows the importance of the materials with time. You know, and why is gold valuable? Yes. Okay, do you think the ancient people cared about it? What is the main reason? If you take all the gold that's on the planet Earth, and please fact check me, how much is that? You're gonna have a cube by what size? Do it now, look. If we take all the gold that's available and make it into a cube, how big would be the size of a cube? You did, yeah, look it up. Look around. This is a brand new room. I really like it. What do we have here? We have a glass. The way it is positioned here is pretty cool. I mean, it's relatively easy to break, and I know how to break it. I'm not going to do that. You also look around, the chairs, the seats are made out of plastic, but then the frame is metal, and then on the bottom you have the coasters that are plastic. So most of the materials are commodities, and believe it or not, but people go to war over that. We have some recent examples of that. Is it?
Yeah, somewhere between 15 and 23 meters.
23 meters.
So 100 feet.
Okay. So my question is, would it fit in this room? 23 meters is not, 23 meters is probably less than to that wall over there. So all of the gold can fit into this building. Think about it. Well, it's cube, right?
Yeah.
This is one of the most important slides, not just for this class, but for all the classes. We talked about the properties, and the guy said a question for you, which one is a property, right? So density is a property, and it's weight per volume. What's the best way to measure density? Using the Archimedes principle, by taking a bath, right? Okay. The volume of the water that's going to get displaced, you can measure that, and then you can measure the mass of the object, and that's how you can. And then how much does it cost? That's another one. So general ones. Mechanical, we're going to have a separate lecture on that, but I build a machine. I build a portable tensile machine for specific applications. And to test the mechanical properties, what you need to do is you need to pull. And now I came in a little bit more prepared, so here's the thing, you can pull. And I'm applying the force, and as a result of applying the force, I get the displacement, right? Okay. So the force can be converted into the stress, right? How? Anybody know?
It's just the original weight minus, or the displacement minus the original weight times the force applied.
And what units would you get?
PSI.
Okay, units of pressure, which is newtons per meter squared.
Yeah.
Where do you get meters squared or inches squared? It's okay, no problem. The stress as the units of pressure, so it's newtons per meter squared. If we take the cross-sectional area of this rubber band, and then we divide the load by the cross-sectional area, that's going to give us normal stress. Okay, that's what you see over here, stress. And sigma means that it's normal. Now the strain is exactly what he said. It's the elongation divided by the original length. What's the elongation measured in? Meters. And what's the original length measured in? Meters. So if you divide meters by meters, what do you get? No units. So strain here has no units. Right? But what are the units of stress? We just discussed that. Pascals, which is newtons per meter squared. Okay, here's $1 million question. If we have the vertical scale in pascals, and we have the horizontal scale that has no units, then what would be the units of this slope right here? We have pascals divided by nothing, so the slope has the units of pressure, and that is the elastic modulus. That's the Young's modulus or modulus of elasticity. It's the measure of the material stiffness. Because every material works as a spring. It acts as a spring. Right? You know what a spring is like? You remember the Hooke's law? F equal kx. What is F? For a spring is the force. Right? What is K? Spring constant. And what is X? The distance. Okay. Is this a spring? Why not? Is this a spring? Pretty good one. Okay? So, any material that you take and you compress, it deforms. So even though it's not a spring, but each material has its own spring constant, which is a mechanical property called Young's modulus or the elastic modulus. And the slope of that between the stress and the strain, that's the elastic modulus. Okay. What happened to that paper clip? Yeah, it's in my backpack, I think. But do you remember the paper clip?
Mm-hmm.
Where's that paper clip? Anybody have a paper clip? All right, I'll use this business card instead of a paper clip. Okay, so what I'm going to do is I'm going to bend it 90 degrees. You see I bend it 90 degrees? Okay. And I'm going to let go. And it restored its shape, right? So what kind of deformation do we have during load? Well, obviously we have elastic deformation, meaning that it's recoverable, right? So if we're anywhere here, we're going up and down, and that's what you want. That's primarily would be your design, is to have an elastic deformation. But then if we take it here, the material starts to deform plastically at a constant stress level. Okay, and that's a fender bender. Okay. So the trick is, because the stress has the units of pressure, then the slope has the units of pressure because the strain has no units. And the actual physical data point here also has the units of pressure, pascals. That's why elastic limit, sigma sub y, has the units of pascals, and the slope has the units of pascals. So the strength or elastic limit, the trick question that I used to ask during quizzes for the last 20 years is elastic limit is measuring what kind of property, elastic or plastic? And it's a trick question. Plastic, who said plastic? Right, because it corresponds to the onset of plastic deformation, although it is called elastic limit. See? The other thing that's kind of tricky for me as a foreigner is the stress versus strain, because they sound very different, very similar. They start with a stress, and strain. They're two different quantities. Strain is relative deformation. Okay. Fracture strength. It's when, if I continue all the way and it actually breaks, that's the fracture strength. So there's a stress level at which the material fails. Another parameter. Fracture toughness. This is a good one. And for that, I'll try to do a demonstration. And next time you go to the bathroom, you're gonna remember me, because you're gonna look at the toilet paper.
What?
Next time you're gonna open a soda can, you're also gonna remember me.
What?
Imagine a soda can. Some states it's called pop. Why is it called pop?
It is?
When you open it, it pops. Okay, there's a relatively thick piece of aluminum on top, right? If I give you, have you ever tried to rip a can with your hands? Don't cut yourself. It's not so easy, although the aluminum is very thin. So how come you can open that can? Why? Shear, but okay, so? Does anybody know? Small, which is achieved how? The lever, that's good, and besides the lever, what else is there? Next time, what? And then what else? It's already weakened. How is it weakened?
It's like a little cut.
Little cut outline that gives you stress concentration, similar to the perforations on the toilet paper. Okay, now, what I'm going to do is I'm going to rip this, okay, and I'm not strong enough, especially holding this. I don't want to be strong enough to rip it, okay? You believe me? I mean, you're probably a strong guy, you'll be able to rip it. But here, look, you see there's a little tear, okay? If I go like this, it's relatively easy to do that, okay? There is stress. How do we calculate the stress? We take the load, whatever force I apply, divided by this area. Okay. Now, once I have a little tear, I still apply the force. And the stress level is, I can calculate with this. And once the crack starts to propagate, the combination of the stress and the crack length give us a material property called fracture toughness, which is equal to stress in megapascals times the square root of a meter. And the square root of a meter is the length of that crack right here. That's why it has weird units. I believe next semester I'm scheduled to teach fracture mechanics. That's what it's about. The next time you're going to drink a soda or go to the bathroom, the reason the toilet paper breaks when it breaks is because of the perforation. All right. Everything, when it's heated up, it expands, except for water. Right? From the mechanics perspective, it doesn't matter what's causing the cell engagement. This, or the fact that I heated it up. So the measure of the strain per degree is the thermal expansion coefficient, alpha 1 divided by Kelvin. Kelvin is a degree. Then thermal conductivity, watts per meter per Kelvin. So thermal strain that you see there on the left upper side versus temperature, and the slope of that is the thermal expansion coefficient. Thermal conductivity or thermal conduction only is present when there's a temperature gradient. It was pretty cold this morning, right? Electrically, conductor versus insulator. Oh, thermal conductivity. We have heat flux versus delta T over X. Delta T is that difference in temperature, and X is the distance. So the temperature, heat transfer only happens when there's a gradient. Brittle materials. We have stress strain curve, and then boom, it just snaps. Versus plastic. So I kind of like showed you pretty much all the properties that there are. I happened to work at Motorola before, and it took tens of years to develop copper process. That's what you see over there. On the right, I've actually taken that picture. What you see over here is aluminum wiring there's a void because when the current density is very high, the electrons transmit the momentum to atoms and physically knock them out of the way. This is why your grandma's house had aluminum wiring, now there's copper wiring. But the process was changed. How? The reason we have a cell phone that has the power of a computer 10 years ago is because there's low resistivity of copper. There's improved resistance to electromigration. So you can run your processor at a higher frequency. There's a smaller chip size, higher power density, the whole 9 yards. There were big problems with the processing. Copper goes into silicon like butter. Copper adhesion, that was my PhD thesis. I measured that. I measured the adhesion of copper to silicon. Other issues, all were solved by the use of a layer. How was the process changed? Here you can see aluminum line and the dielectric, which is SiO2, it's glass. It's an insulator. Aluminum is a conductor. SiO2 is the insulator. The first Pentium processors were like this, probably around the time when you were born. Now it's copper, but the difference was that the process was changed. The first, they dig a trench, then put 2 proprietary barrier layers, which you can find out about what I'm telling you. And then they electroplate. So this was done in vacuum. That is done in a copper sulfate bath. So what controls properties? From one atom, it's the electronic structure. It's that chemistry stuff that we're still going to do. The s electrons, the p electrons, the d electrons, and whatnot. And then how they are bonded together. Covalent, metallic, ionic, 3 major types of bonding between the atoms. And then how they're put together. This is all physics. And then how fast, that's kinetics and that's material science. And that's where we get into the structure properties relationship. That's where the defects come in. Periodic table of the elements. This guy, Mendeleev, was a genius. He also invented vodka, in case you didn't know. Great chemist. He put this periodic table together. And you've seen this before. So when I came to graduate school, a material science professor would give us an element, and he would, and I didn't understand why am I supposed to memorize it when it's in every class. Now I can appreciate why he was forcing us to memorize the periodic table, specifically around silicon. Because most of the elements are conductors. And some of them are insulators, and some of them are semiconductors, which means that they can go both ways. So if you look at the two atoms start to interact. If you pull them away from each other, they're trapped. If you push them towards each other, they repel. This is in terms of the force versus distance. This is in terms of the energy. So if there was no help session today, where would you be? Not here.
Home?
Okay? So every system tends to go towards the minimum, and this controls properties such as elastic modulus and the bonding. Strong bonding versus weak bonding for individual atoms. Okay? And the guys mentioned crystalline versus amorphous. Crystalline, imagine a big pile of bricks that's arranged in a periodic array versus randomly distributed. Which one is going to occupy a larger volume? So what you see here on the left is quartz. It's SiO2. So the backbone of the structure is the same. It's the SiO2 tetrahedra. On the right, that's glass. So long range order versus short range order. And for the amorphous solids, the reason materials can be amorphous is because they were frozen very fast, or because the molecules are too long to rearrange in a periodic array, which is also possible. And then we're going to talk quite a bit about the crystal structure. The way the atoms are packed as hard spheres. And the best way to pack is take your 3 fingers together and put another finger right here. You cannot pack atoms or balls of the same size denser than this. But the trick comes, let's say this is layer A, this is layer B. So this is layer A, this is layer B. You can see this atom goes right here. Do it so you remember. And then the question is, where the third layer goes. If the third layer goes into the A, B, A, then you have what's called hexagonal close packed. If the third layer goes into another configuration, which we call layer C, and I'm going to bring the models to show you this so you can play around, then that's going to be phase centrocubic structure. The packing is the same, but the properties are severely different. And how do we study that? We study that by X-ray diffraction. So those planes of atoms, they diffract X-rays. And those X-rays have a specific wavelength. Remember, we were after a certain length scale? Okay? Next time you go to a dentist, it's kind of like that, except that they take an X-ray of your teeth. The wavelength of X-rays is in the angstroms range. And the atoms, or the distances between the atoms, are also in the angstroms range. This is why the radiation matches to that atomic scale. And here it shows you like different kinds of defects that we can study using that. Again, I'm giving you an overview of the whole course, pretty much. But you remember this game? There are 15 squares, and one of them is missing. You're supposed to put a puzzle together. You know what? You know, do you know what I'm talking about? In other cultures, it's called the 15 because they're numbered 1 through 15. Here, it's typically some sort of a cartoon puzzle, right? How can you move them? Up and down, but one at a time, right? One square at a time. There's a very big difference between diffusion in gases versus solids versus liquids. How does diffusion happen in gases and liquids? Let's say I sprayed perfume here. I just sprayed perfume. You're going to be able to smell it over there after a certain time. How does that work? What did they tell you in physics? Brownian motion. Or we can take glass with water and we can put a dye, and after a certain time this dye is going to spread around. There are very many different degrees of freedom for a gas versus liquid. But for the solid, we're back to that game. Because in order for an atom to move, here, there has to be a space. Okay? This is how it works. You can move to this chair. You can. Then that chair is going to be vacant. Or you can move to that chair. But you cannot move into this chair because he's already sitting there. Likewise, you see that? This is why in the solid things are much more restricted. And we're going to talk about how diffusion happens in the solids. Equilibrium. Mechanical equilibrium. You can see there's one on the left. That ball is sitting there. It's in equilibrium. But there's a lower energy state on the right. But in order for this ball to get from that pole to this hole, it has to overcome that energy hump. So, the first law of thermodynamics. Have you taken thermo yet? Yeah. The internal energy of a gas is 3/2 nkt. T is the temperature in absolute units in Kelvin. K is the Boltzmann constant. So the atoms are sitting there at room temperature, they are vibrating. The natural frequency of a vibration of atoms is 10 to the 13 hertz. Can you imagine? That's how fast they vibrate. Any vibrating system has two parameters associated with it. What are they? The frequency of the vibration and the amplitude of the vibration. That's how the energy is stored. Okay. So the work that's done is PdV. P is the pressure. dV is the change in the volume. So we can write that dE is equal to the dQ minus PdV. And enthalpy is the heat absorbed at constant pressure. So H is equal to E plus PV. That system heat capacity, C sub P is dH dt, derivative of the enthalpy with respect to temperature. And the heat absorbed at constant volume is dE dt. Now, because liquids are incompressible, then we can write that PdV term is constant. So internal energy is equal to enthalpy for a solid. The second law of thermodynamics talks about the direction of those spontaneous changes. The first one means that the energy is conserved. You're not losing or gaining any energy. The second one means that there's mixing energy, which is a product of the absolute temperature and the entropy. So that entropy delta S is equal to the K times log omega 1 over omega 2 here. That's number of the distinguishable states. That brings us to the concept of free energy, delta G. So for equilibrium, delta G is equal to the delta E minus T delta S. Okay? And that brings us to a very important concept of the concentration of defects in a solid. Okay? How many of you like a drink? Hot drink or a cold drink? Which one do you prefer?
Why not hot chocolate?
It's a good one because it has sugar. Okay. Do you realize that for the hot sugar, for the hot chocolate, you can have more sugar in it than at room temperature? Because there's a temperature dependence. So if we look at the free energy, this is the linear term of internal energy, delta E times N sub I. N is the number of defects. And this is T delta S at different temperatures. So we add them together, and that gives us different concentration of defects at any given temperature. That's where we get the solubility curve. That's where those phase diagrams are going to come from. So from this, we get temperature versus impurity concentration. And that's what it's all about. It's all about defects. How many defects can you have in the system as a function of temperature? By the way, if you have a function, what's the way to find the minimum and the maximum? You take a derivative, right? And what is the physical meaning of a derivative of a function? It's the slope, right? So if the function has a maximum, the derivative is equal to, or minimum, the slope is equal to 0. That's why we said that that's the physical meaning of a derivative, right? We take a derivative, we set it to 0, and that's how we're able to calculate the number of defects. Now, this guy's told you something about phases. Single phase. Water has 3 phases. Water, ice, and vapor. Gas, solid, and liquid. It's a simple system. It consists of H2 molecules, right? And now we can add some stuff to it, like Mendeleev did. Alcohol. There's unlimited solubility of water and alcohol. So you can have 100% alcohol, you can have 100% water. But if you add salt, at some point salt is going to what we call precipitate. You cannot dissolve any more salt in water. You know what I'm talking about, right? Now some phases never mix, like oil and water. So next time you buy that dressing for the salad, which has vinegar and olive oil, you're better off buying them separately. Or before you put it on your salad, you have to shake it. And you form a suspension because neither one dissolves in the other. Okay, kinetics. This chair, look at this chair. If I flip it like this, then that's a lower energy state of the chair compared to when it was standing up, right? But in order for me to do that, I had to go through this little tiny energy hump, delta G star. We call it activation energy. So you spend a little bit and you gain a lot. So there's some calculation. Remember that 10 to the 13 hertz? That's how fast things can happen at room temperature. That's the number of attempts that there are. And then we have metastable states, meaning that this chair is going to be sitting like this for the rest of its life, for the rest of our life, until somebody comes in and kicks it. The same thing happens with the materials. Like this metal, there's going to be energy gain if it is in the form of an oxide. Okay? And then the famous Arrhenius equation. The rate of the reaction is equal to the A times the exponent of minus delta E over KT. You know how I learned stuff? I learned stuff by doing it. So I have about 7 minutes, and I want to show you something about the Arrhenius equation. You know what they're making? Hard drives. You know, and now they're like a lot of terabytes. The first terabyte hard drive came about 2006, 2007. Is there any way to show it? Measure evaporation rate of oil. I'm like, what are you talking about? So the first hard drive, which was 1 terabyte, back in the day, had a little tiny drop of oil. This is the Arrhenius equation. The rate of the reaction, in this case, the evaporation rate is equal to a constant times the E to the minus E over RT. E is the activation energy. So we did this experiment. But before, what you do is you take natural log of both sides of this equation. Please get yourself familiar with this mathematical procedure, because we're going to use it a lot, right? You take a natural log of both sides of the equation, and if you take 1 over t as your x, then this becomes what? A linear equation. And you know, people tell you this stuff, but I only learned it when I was doing this experiment. So you see, this is a log of K of evaporation of oil versus 1 over T, and this is the data. So we were able to calculate the activation energy for evaporation of oil, and we did it both statically and dynamically, meaning that the temperature was kept for 2 hours constant. Oil doesn't really evaporate that much, unless you start to fry it really bad. And you can see there's like extrapolation of continuous versus, and that way we were able to calculate the activation energy for different alkanes. And before, they had a person who would have a hard drive on a hot plate at 100 degrees for 6 months. So didn't they have good job security? And there comes Alex, who can do this test in 1 day and qualify the oil. This guy wasn't happy about that. Nate Wolstein works for Air Force now. And then we actually made, because in the hard drive, there's a very complicated geometry of the motor. So we made a thread and made the oil evaporate through a spiral channel, threaded and non-threaded. So there you go. Do you have any questions? All right, so the idea of this help session is to solve the problems. Because I can lecture all day long, you know what I mean? There's no reason to go.
Definition of on what material science and engineering is. Yes.
Study of material characteristics of certain environments,
And what about for materials engineering?
How, in those specific environments, how would they fail in mechanical systems?
Anyone else want to have or share your definition for it? Just kind of a recap a little bit from class year you had. Those are good definitions, by the way. So, just like he mentioned earlier, material science is the investigation of relationships between structures and properties of materials, and you use those, what you know about the material, to help you build new materials. And materials engineering is you're creating products from existing materials, and you have to process those materials using certain processing techniques so you get the most out of it. And I'm sure you guys understand the importance of materials and why they're important, right? Does anybody care to give a definition on why materials are important? All right. So basically assessing the characteristics, properties of that one material that you're thinking about using, you can use that material. So materials are drive advancements in our society. So you have like preamble, Stone Age, the Bronze Age. So different stages where materials kind of become important, where we start to master different processing techniques. And just to recap with everyone, why is it important for engineers to understand materials? We kind of get. Yeah, that's a good definition. So, right, so we'll learn this a little bit later, but, so just as you were saying, like, you gotta pick the right material. Is it cost effective? Is it environmentally friendly? Is another one. Is it easy to make? Is it, like, for example, like, you can't just throw titanium at everything. Or like steel at everything. Maybe just a good old fashioned plastic, or maybe not even plastic, maybe your material or your application needs like a ceramic because you're dealing with high heat or something. So you gotta make sure you're considering the type of material and what you need it to do, but also it needs to be able to be processed cost effectively for the application that you need it for, and it's also filling in the other gaps as well. I guess to go a little bit further into that one, I'm sure you guys have already seen this slide. The importance of it again is the products, devices, and components. Basically, depending on what you're trying to apply this thing that you're building to, you got to pick the right materials, otherwise it's not going to work. And it relates to the structure-property relationships. So, for example, like processing, when you're cooling steel, the structure, the microstructure changes, and that structure in turn affects hardness. Do you guys know what hardness is? Yeah.
How compact would be molecules on?
Huh?
How compact, how dense the material is?
I can kind of see that definition. Any other? Yes. close. It's kind of like that. And then I think there's a hand in the back. Yeah.
Is it the materials ability to use and
Mm, almost, kind of. So I guess, so that's easy definition for it, I think would be surface strength. So I don't think you guys have seen this yet in your classes or in this class in particular. But there are special like indentation tests and things like that you can do to materials to figure out how hard it is. And then based on all that, it'll tell you the strength of that material when you try to make an indentation into it. So I was hearing like compression and stuff, so they were almost there. But that's the definition for it. I think you guys are gonna learn more about that later in this course. And then we already went over this. And this part here is, I'm assuming new for you guys, the material selection part.
He's right outside. That's why I get problems.
Determine the best materials to use for your application. Yeah. So, if I heard correctly, basically assessing material properties, right? That's good. Anything else? Yeah. Say it again? Budget. True. I guess budget would be more, I think, of like the last step of the process, kind of. So without thinking about money or anything like that, what would be some things that you would want to consider in the initial stages of building something for some application? In terms of selecting materials. Yes. Right. So for a specific application, you want to determine, like how everybody was saying, specific required properties that you need, like mechanical, electrical, thermal, etc. So it all depends on your. So what would be the second thing that you would do in order to determine what materials you want to select for your application? So the first step is we're determining already what properties we want for our application. So now what would be the next step? Yes. Right, so then the next step would be from the list of properties that you've listed out for yourself, you would then try to figure out the best candidate materials for that. And what would be the next step, and I guess in this case our final step, because I don't think there's that many slides for this. So what would be the third step once you've created a list or identified your candidate materials? wait, say again? Right, correct. So once you understand, or once you know what the best candidate is for the thing that you're trying to build, you would then specify your processing techniques to actually make it. And I believe the gentleman here mentioned like you would then consider like things like cost, how easy it is to fabricate, what technique am I going to use to actually form this material, like for example casting, mechanical forming, etc. And to have a little fun with it, speaking of material properties, off the top of your head, does everyone know what the material properties are, or the different, I should mention, categories of material properties that you could consider when you're building something? Yes, electrical is one of them. Another one? Yeah. Optical is one, yeah. Thermal properties. Any other properties? I think that's 3. I hear 2 more. And I think there's 1 more that you guys understand. That's pretty good. Right, so how does a material deteriorate when it's out in the environment? So like, if I'm not mistaken, it's steel? If you leave it out in the rain, it'll start to rust and oxidize and stuff. So you have to alloy it or put some sort of coating on it so that it doesn't rust out on you on your application. So good job, so we know the different material properties. And here we kind of touched a little bit on mechanical already in our earlier slides. We were talking about hardness. And basically, as you increase, in this example where you have common steel, as you increase the carbon content, the hardness goes up. For electrical properties, and so an important relationship to know with like electrical properties. So as you increase temperature, as it says here, resistivity will also increase. So there's a relationship between thermal conductivity and also electrical conductivity, at least for metals. So usually as you increase the temperature, the resistance will also increase in the material. There is a material though where, I guess I'll talk more about that with thermal properties, so I'll have hold on to that thought.
Do you guys have access to Wiley Plus?
Right.
Just pull up some problems so that, you know, maybe you can go over some problems, because you've seen the slides.
So in Wiley Plus, or at least for the introductory slides, there isn't a whole lot of questions.
Let's go to the next chapter. Do some problems. Pull up some problems.